We've been hanging out for many years, although he's rejected me as of late and has not been hanging out. So we're just very fortunate that he would come to Augusta here. I have a pretty good idea of what Tim's going to talk about, so let me just point out that the fail guys, they've got some really cool stuff over. No, but seriously, if you see something, if there's a talk that interested in this one, Tim's talk is going to be here.
It won't hurt my feelings if you walk out.
The fail guys, they got the lock picks over there, and they're over in UH-170 in the areas right in front of the blue teamers. You know, you get the blue teamers picking the locks, and then they're like, "Ooh, this is really fun." Then they come over to the red team talk. It's like a gateway drug, right? That's what we're doing with it. But with that, welcome Tim Tomes.
Hey, thank you, Mr. Mark. I love Augusta. Don't let Mark, give you guys a misconception of how I feel about Augusta. I spent a lot of time here, actually, about 6 or 7 years of my career, military career, was spent in Augusta. A lot of time before board. Anyway, before I jump into mine, I want to caveat something that Chris Grunster said in his last talk real quick, and it's about mentorship. Right? I'm a firm believer that mentorship goes both ways, and that everyone at all times is 2 years behind someone else in their industry and 2 years ahead of someone else in their industry. So you should simultaneously be mentoring and being mentored at the same time, at all times. Okay? That will provide maximum growth to this industry. I encourage that to all the folks that I mentor, right? And I'm constantly seeking those above me, like Mark, right, that have been doing this a lot longer than me, constantly seeking their mentorship as well. Because, like I said, it goes both ways. And that's the best way that we will enhance our industry. Okay. So earlier this summer, I got an email from the guys at BSides saying, "Hey Tim, you're going to talk at BSides this year." I said, "I don't know. BSides getting kind of old. I'm sure most people have heard of it by now. If not, they've kind of seen something online, me tweet about it. And frankly, I don't think it's all that cool, to be honest with you. I've had people disagree with me. When you stare at the same code for 2 years, it's not cool anymore. All right. As Chris can verify that. Right. It gets old after a while. Right, so Recon Engine wasn't cool to me anymore, but I was starting to play with the Adobe breach data that came out last year, and there was some kind of fun stuff there. Nothing new, nothing groundbreaking, nothing that no one's ever seen before if you've read any articles about it. But I was tinkering around with it, and I said, there's some lessons to be learned in here. I'll talk about this. Put the slides together, and I had about 15 minutes of content. I'm like, well, this is not going to work. This is after the CFP was accepted, right? So I went back and started thinking about it, and week after week we see these breaches come out, all this data being dumped. Troy Hunt is constantly tweeting about it. There's other folks. Every week there's information being dumped by hackers that are breaking into websites and stealing credentials. Right? And I got to thinking, well, this is a huge problem. Why don't I just give a talk that addresses this issue, and then maybe somewhere I'll turn on a light bulb in somebody's head, and we'll start to turn this problem around. So that's what this talk is about. We're going to talk about stored password security, and we'll also talk a little bit specifically about the Adobe dump and some of the work that I've been doing there. That's for slides. Okay. So who am I? Well, I'm not going to go into any detail. Just know that all this middle stuff I'm doing to achieve this bottom bullet, and I'm hoping while I'm doing that I'm glorifying the staff here in the upper left-hand corner. So I'm going to give a quick shout out to my buddies at Proper Attackers and Hackformers while I do that. All right, the agenda. Don't want to spend a whole lot of time talking about the agenda because we're going to hit all of this while we're in it. So we're going to talk about some misconceptions here about these 3 items at the top. We'll address the problem. And then we'll break the problem down into different sections here. As you see, we've got 5 different iterations we're going to go through. We'll talk about different implementations of stored password security. Talk about the individual problems that lie there. Talk about some solutions, and hopefully by the end of the day, we'll all be much, much better at storing passwords in our backend databases. Okay? So disclaimer. I'm not a crypto guy. I don't know anything about crypto. The reason I wrote Recon Engine is because it's simple, it's easy, and I'm not that complex. All right? So, if you see something that's inaccurate here, okay, that's fine. Come forward, please correct me afterward. Please don't be a crypto snob on me. I can't stand crypto snob, and I'm not going to call you out on it. But just be nice about it, because I don't know much about crypto, and I'm admitting it to you right now. But the beauty of this thing is you don't have to know a lot about crypto to store passwords properly. Right? You don't have to know a whole lot about crypto to identify when somebody else has done it wrong as a pen tester and exploit that flaw. Okay? So that's the first disclaimer. Second disclaimer is offensive material as possible. For any of you that have seen a Recon Engine talk before, when we start dumping passwords, you start to learn stuff about people you didn't want to know. Alright? And so you may see some things in here that are slightly offensive. Please, big boys, big girls, we all know what we're getting into here. Please don't send me any emails or email. I appreciate it. Okay? So, misconception here. Encoding is not encryption, it's not hashing. Okay? Now, you're right in saying that, hey, every single one of these transforms data. They all have something in common. You're absolutely right. They have something in common. They transform data. But they have very, very different reasons for transforming that data. And I'm hoping that everyone in here, as a precursor, I had to script like 15 minutes out of this talk. I was going to break each one of these down. I don't have time. So I'm hoping everybody understands these. But basically, encoding transforms data so that it can be consumed by alternate information systems. Okay? Right. Encryption transforms data for what? Confidentiality, to prevent eavesdropping, right? Prevent someone seeing it that wasn't intended to see it. And then hashing is for validation, right? We want to validate a piece of data in 2 different places. We can use hashing to do that, right? So these concepts are extremely important. But the problem is developers are still applying these concepts wrong when they're implementing stored password security or secure stored password storage systems, okay? How many CISSPs do I have in here? You should see a whole lot of CISSPs because we're in a fairly heavy government area, and that's kind of one of those regulations, right? But it's been a while, so I don't know what it is. But anyway, this is CISSP level stuff. This is entry level security, okay? And the simple fact that our developers are still doing this stuff wrong means that they don't have even the basics of security in their development practices, okay? And that's a huge problem. And when we break AppSec down all the way to this root level, this is the problem. No secure coding practices training for a lot of our developers. Okay? Huge issue. Second problem is when our developers create a system that stores passwords insecurely, these guys step in and mop it up. Anybody know who these guys are? People seen these folks before? Breach Alarm is a fairly new name. Should I change my password.com rebranded to Breach Alarm? Okay? Pwneless, and this is Have I Been Pwned by a website by Troy Hunt. What these folks are doing is when the hacker breaks into your network and dumps your passwords to the internet, these folks are going and collecting them. Now they all have a noble cause, right? They all provide this pretty little form that says, put in your email address and we'll let you know if you've been pwned. Alright? But in the background, I'm convinced that most of these guys are storing that data. And they're using it in other places. Right? I know for a fact Troy Hunt is storing it, but he's not selling it, he's not distributing it, and he's doing it because he doesn't want to be the guy responsible for that. I trust Troy Hunt, because I know him well, and he's a really good dude. Breach Alarm, don't know these guys at all. They say that they don't store that stuff. I don't believe them. Alright? Pwneless does store it, and they'll sell it to you. Okay? Pwneless is selling that stuff. It's ridiculously expensive for those of you that have ever gone and looked at what it costs to gain access to their API, but it's not cheap. It starts at about $60,000 a year. Alright? And that's for 1 million requests, which goes really, really fast. Alright? Especially since it's 10,000 requests to dump it into the domain for the data. So, alright? So these guys went out and storing that data and then making it available, which means now you have all of this information that's being harvested and possibly sold off to what? Third countries that are adversaries, right? Or maybe some adversaries with some funding, right? So some sort of sponsorship there. Yeah, it's expensive, but it's accessible, and that's the point. So we've got a problem. Now what I want to do is I want to go into a couple different password store systems that I encounter while I pen test, and I want to talk through each of them independently, kind of show you an example of what they look like, and then we'll dig into some of the problems, specific problems and solutions of how we can fix this stuff. The first one I want to talk about is Encoded, or Plaintext and implementation of stored password security. I call it stored password insecurity. Okay? And basically, it's real simple. Here's our user table. We got a username, and we got a password, and the password's in clear text. So it's literally, like here, you're going to see some pseudocode under each of these diagrams that I do. Typically, we're trying to create some sort of protected form. I refuse to put protected for this, because it's not, right? It's just straight up clear text. Really simple. So, what are some characteristics of this? Well, man, you got a really simple password recovery system, right? All you have to do is say, hey, I lost my password. Here's, the answer to here's the name of my first pet, and well, here's your password. And they can give it right back to you. You don't even have to change it. You don't have to go through a complex email swapping system or any of that stuff. Real simple password recovery system. These folks are typically, folks doing this get caught real quick. How many of you have seen a password in your email before? Your straight up password sent to you, right? Those people should be on plaintextdefenders.com if they're not submitted. Because that's what they're doing, right? If they can give you your plaintext password, they have to have access to the plaintext password. Okay. So it's functionally simple, yes, but incredibly unsafe. The next thing is, because of this, we have unpredictable resource requirements, and this leads to length restrictions. Well, what does that mean? What if I create a 10 gigabyte password? You going to store all that? And what if you don't have 10 gigabytes of space within your storage? Okay? Yeah, can I conduct a denial of service attack against your database or against that server because I fill up the hard drive by slamming huge passwords in there? And so what happens is these folks go in and say, well, we're going to institute a length requirement. Okay? And what does that end up being? About 8 characters? Yeah? Ends up being about 8 characters, right? And then we say, oh, and by the way, you can't use exclamation points, single tigs, double quotes, or anything which screams SQL injectable, right? So we have this problem here that we've got unpredictable resource requirements now, and that leads to length restrictions, which what we can are passwords. Okay? And then the major problem with this implementation is there's absolutely no effort required to get to the clear text password once a breach occurs. When a breach happens, bang, clear text passwords are out there. So who here knows who Cuban Media is? Okay, the first person that's brave enough to raise their hand gets this book. All right, that guy back there. You're an online data, aren't you? It's right here on this chair right here. Okay. So yeah, Cupid Media, they run about 35 different niche dating sites. Well, in 2013, November 2013, they got breached and 42 million clear text credentials were dumped to the internet. Bam, just like that. We got passwords, right? And a whole lot of people were dating people that they shouldn't have been dating. Right? So let's see what this looks like. Let's demonstrate the risk of this type of storage system, right? Using ReconNG. So Mark lied. I am going to use ReconNG today. We are going to talk about it because I'm going to work it in every talk I give for the next several years, probably. All right? So let's go in here to ReconNG. Who do I like to pick on all the time when I do ReconNG demos? NSA. The NSA. Let's do it. All right. So we'll create a workspace. Call it NSA. Let's add a domain. What's NSA's domain? Yeah, NSA.gov, right? All right, so the first thing I do, how do we get access to credentials in ReconNG? I'm going to use phoneless. All right, there's lots of different ways to do it. You can go out and mine it yourself, right? You can talk Roy Hunt into giving it to you, which he's not going to because I tried. Right? There's a bunch of different ways you can do it. But since I develop and I've got a relationship with Phoneless, I have access to the API. So I use Phoneless to do this. So I've got a module, I've got a couple of modules that do this. You've seen me demo before. But the first one I use is a module called isPwn. And basically what it does is it queries Phoneless and says, hey, do you have any credentials for this particular domain? So let's load the isPwn module and run it. And it tells us, yes, I had 284 phone accounts for NSA.gov. And the last time it was seen was August 26, 2014, which was, what, like 2 weeks ago? Right? So there's some pretty recent, pretty relevant data in there, right? So I'm going to go ahead and dump that. By the way, this was one query. This next one I'm about to do is worth 10,000 of those 1 million tickets you paid 60 grand for. All right, so let's load domain creds. Now let's run this. And we are pulling down creds.
Hey, here's my email address.
I wouldn't be surprised. In fact, if any of your employees at the NSA, we can look you up right now. It's going to make a fun demo. Okay, so looking through here, right, we can already see that we've got clear text creds, right? That's it, plain simple. No more work other than that. All right, we've got passwords, and all we did was query their API and pull them down. And there's quite a few of them here. We can scroll up here, we see those. We still got some hashes and some other stuff going on. We'll get into that here in just a few moments. But what I wanted to demonstrate here is there's a lot of risk in that. Because all Phoneless did was go out to the internet, probably paste bin, download them, parse them, put it into a database, and now I've got this information. Okay. So some serious risk in using, in storing your passwords as clear text. So what are some solutions? Well, a solution I've seen is to use encryption. All right? Let's encrypt our passwords. In fact, I saw somebody wearing a shirt. Is the person here that's wearing a Wall of Sheep shirt? Can you stand up for a sec? Can we read the back of your shirt? What does it say? Somebody read it. It says, encrypt or you'll regret it in the end. That's a lie. It should be use adaptive hashing functions or you'll regret it in the end. And we'll get to that here in just a few minutes. But encryption will get you owned, and we'll talk about that. All right? So what about encryption? It can look somewhat like this. This is an example I've seen in a mobile assessment that I did about a month and a half ago. Okay? AES 120-bit is the algorithm here. The key is secret, okay? Quick, mention something real quick. Most of the time when I see encryption implemented in stored credentials or credential storage systems, it's using symmetric encryption. Rarely ever have I seen, in fact, I can't name an instance where I've seen asymmetric encryption used here, which means we're dealing with an algorithm and a key, right? One private key and an algorithm. Okay, so here we've got AES 128, and there's our key secret. That is the actual key that was used as well, right? I mean, is that less secure than the actual word secret? No, it's the same kind of letter, but it's close. All right, but you see here, we've got our pseudocode here. We're passing in our password, our key to the encryption function. It encrypts it, and then encodes it, and it sends it in protected. Now, the reason why it encodes it, right? You don't have to do it this way. Like, you can store binary data You can store binary data in your database. However, most of the times I see it stored as plain text in some sort of varchar field within the database. And so in order to do that, they've got to encode it into a different form that is consumable by a plain text field. And in this particular case, it's base 64. So here's an example of encoding versus encryption. The encryption happens here. All the encoding does is change it so it can be stored there, but that's easily reversible back to its binary form. Okay? So here we've got our binary blob encoded and stored in the database. So what are some characteristics of this? Once again, a real simple password recovery system, only slightly more complicated. The fact that now you just have to reverse it with the key, but they own the key, right? So you say, hey, I forgot my password. The name of my first pet was bear, okay? And then they send you your password, your email. So once again, this is still unsafe. This is almost the equivalent of storing it in plain text from a protection on the server side standpoint. We'll get to that here in just a moment, okay? So other characteristics here is you have to be concerned with encryption key storage. Okay, we'll chat about that more in here in just a few minutes. Once again, we got unpredictable resource requirements leading to length restrictions, because in most cases our ciphertext is in some way related to the length of our plain text, okay, when we're dealing with encryption. So we still have that problem that we have to deal with, and what do? We end up loosening the restrictions and creating weaker passwords as a result. Okay? Something very, very important about using encryption systems. There are 4 elements to this. Okay, your security is based on both the algorithm that's used, the cipher mode that's used, the key storage system, and the key itself, the strength of the key itself. And those are 4 items that we're going to revisit every time we talk about encrypting passwords for our database, for our storage systems. Okay? So what are some problems with this? Well, you got the key, you can decrypt the credentials. This depends on the level of access, the level of compromise of the target, right? So if I compromise the server and all I have is SQL injection against the user table, I may be able to pull the creds, but I may not have access to the key. But if I'm coming in through the network, I'm looking for the key. And I'm going to try to find out where it's stored. I'm going to try to gain access to it. If I've got access to the source code, I'm going to try to find out hard-coded there. A lot of different ways to approach that. If that's not an avenue of attack, then maybe we can take advantage of weak algorithms or cipher nodes. Okay? So let's jump over to the solutions to that now. Let's talk about a case study. Anybody remember this? Yeah? Largest data breach from a single source in recorded history. Now I'm waiting for someone to say, Russia released 1.2 billion last week, or last month. That was 420,000 different sources of passwords, okay? Single source, Adobe's still the largest. Who has a username that was in this dump? Okay, you get a vote. Everybody was in this dump, right? I know that he's not the only one. There's only 2 people that raised their hand. There's probably about 90% of this room is in this dump. So huge password dump, okay? And so what we're going to do is Adobe used encryption, right? They used encryption to store their passwords. All right, we're going to go through, we're going to break it down according to those 4 elements I talked about in the first slide, and kind of break down their issue and find out where it happened. So, first we're going to look at the key components. Remember there's 4 of them. Key storage mechanism, key strength, the algorithm, and the cipher mode. Well, in terms of key mechanism and key strength, they're unknowns to us. Okay? Now, one thing that's really, really interesting to me is that Adobe claims that it was a sophisticated attack on the network, right? And then it led to access of customer information and source code. If I had that information, I got the key. If I got this much access, I'm not leaving without the key. So either they didn't release the key, or they didn't bother looking for it. They just wanted to find Adobe. Alright, which they did a pretty good job of, okay? So the storage mechanism is not known here because it wasn't disclosed. Kind of the same thing with the key. They didn't disclose the key with it. Adobe didn't tell us what the key was, and to my knowledge, no one at this point has actually cracked the key. I'm not working on cracking the key. What we're going to talk about is kind of a different approach to cracking passwords for Adobe. I'm not cracking the key. If somebody wants to go for it, that's fine. But at this point in time, it's not been cracked. We don't know about it, so I'm going to assume it's a strong key. So these 2 particular areas right here, Adobe's doing all right. We assume they're doing okay. We've not found a problem yet. So what about the algorithm? Okay, well, let's start to break these ciphertexts down to try to determine what the algorithm is. You see right off the bat that there's definitely some pattern here of recognition, right? But the first thing we want to do is we want to break it down into hexadecimal form. And when we break it down into hexadecimal form, we immediately see we got 16, looks like to be 16 character blocks, right? In this particular case, 16 characters is 8 bytes because it's hexadecimal, okay? So we've got 8-byte blocks, right? Well, 8-byte blocks equals 64 bits. And we have a couple of options when we talk about 64-bit block ciphers, IDEA, DES, and triple DES. So this is where we were at in determining which algorithm was used when Adobe came out and said, yes, we were using triple DES. Okay? Is triple DES still approved for use in the United States government? Absolutely it is, right? NIST approved in some cipher modes, not all of them, But in some cipher modes, it is approved for use by the United States government. So what do I say? This is not Adobe's problem. The algorithm is not an issue for Adobe. So they got 3 out of 4 right at this point. Okay? They're doing okay. So before we jump into what mode Adobe was using, let's talk a little bit about modes. Alright, so there's this thing called electronic code book, and then there's everything else. Alright, electronic code book is known as the raw mode, or a raw cipher mode. And the reason why is because there's absolutely no chaining involved, and there's no initialization vector. You don't have to be a crypto person. I'm going to tell you what an initialization vector is. It's randomness that's introduced to the encryption process to prevent information in, the same information in, appearing the same when it comes out. Okay? So if I have random data going into all these, kind of like Salted+Hashed, for those of you that, we'll talk a little more about that here in a little while, but it's randomness going in that affects how each block along this chain looks. Okay? Right? So it's completely wide open, which means if I had the same ciphertext in the first block, different in the second, and the same in the third, right? Or plaintext, I'm sorry, going in. Plaintext in the first and the third, but not the second. Well, the ciphertext of the first and the third block are going to be the same. And so I can start to see patterns in this, right? And if any of you have seen ECB mode encryption done on an image, and what it looks like after it's been encrypted, anybody look at an example of that? It's wicked cool. You can still see the image. Because all the patterns are still there, the colors just change, right? So it's really, really interesting. This is bad, okay? So let's look at what Adobe's doing. Doesn't take us long to find out that we've got repeating blocks. This is the top 10 passwords in the dump. Right here, the top 10 most common ciphertext in the dump, broken down hexadecimally, and I took the blocks out and sorted them. We can see we've got repeating blocks already. And we can actually look at the ciphertext right here and see 1 through 8 is exactly the same block. And then here, which is our null byte character padded out to 8 bytes, is the same. Okay? So we're working with ECB here, and this is where we're going to bust Adobe in the forehead. Okay? This is where their problem is. So how are we going to crack this knowing we're using ECB? 1 out of 4. Another quick note on this real quick. Defenders, got to be right 100% of the time, right? Attackers only got to be right once. And this is our goal. You did 75% of the way right. This is why encryption is not the answer, because there's a lot of moving parts. You've got 4 different things that you're concerned about here, and these are just the upper level things. When you start digging out each one of these, you've got to really know your stuff, okay? So here, you've got 4 things that can go wrong. It's more complex than it needs to be, and we'll see moving forward. But this is the problem. This is how we're going to crack it. First, you just select a random ciphertext that you want to attack, or it doesn't have to be random. It could be your CEO, right? It could be a target at the NSA. Anyways, then you go in and you analyze the hints. Well, wait a second. Where do these hints come from? Guess what? This breach included all the hints to everybody's passwords. Okay? So we've got additional information baked into this particular breach that really helps us in attacking this ciphertext. You can analyze hints in a couple of ways. You can look at the full ciphertext. Okay? We can just search the dump for the full ciphertext and look at all the hints associated with that full ciphertext and try to break the whole thing at once. However, there's some ciphertext that don't have hints. Right? Some people just didn't put hints in there. And so in order to break those, what you can do is you can break them down into the individual blocks and then look at the hints for other passwords that use those blocks and then start to break apart chunks of the clear text. Alright? And so you're going to see as we go through this demonstration here in a minute, we have bits and pieces of passwords, a lot of different passwords. We have some that are full and then some that are bits and pieces, and we can start to build this thing. Alright, so as you guess, when you look at the hint, you start to guess the plain text. You start to go back in there, you take all those new blocks, you apply them to all the passwords in the list, you start unlocking chunks. Okay? Think of it as a huge Sudoku puzzle, right? Or the world's largest crossword puzzle, as the famous cartoon that like to often put it. Alright? I think you know these CEO's passwords. So what does this mean right here? First thing I did at Invisium was I was sitting there one night, I'm like, man, I wonder if Invisium's got any stuff out there on this, just horsing around. Dumped it, one credential. The one credential was the CEO's. And it was in this one right here. I didn't have any blocks unlocked to decrypt any of his, to reverse his ciphertext at that point. So I went back, used some of the hints from other people, because he did not put a hint in there. Was able to crack his password. It was 12 characters. Emailed it to him and got an interesting email back the next day. But in my line of work, that kind of stuff is somewhat encouraged, especially since I was already hired and I wasn't sending a message that said, you need to hire me or I'm going to blackmail you. No, it was fun. And then for those of you that know Jack Medina, who is the CEO of Invisium, really cool guy. But he was good about it. But that's how this attack goes down. And so let's go ahead and run through a demo real quick of what that looks like. So the first thing I want to do is, let's go ahead and open up a new terminal window. Start a Python interpreter. import Adobe. This is a Python library that I wrote, and I'll be open sourcing it today as well. I want to create an instance of my class which does all the work for me. Oh, can't do that without getting the name of the database. Alright, so this is just quickly what this particular library does. It allows you to crack hashes using uncipher blocks, so you give it a JSON dictionary, cipher blocks, it'll crack it. You can create a block database, a JSON block database based on all the stuff you've already, all the plain ciphertext you've already cracked within the database. You can do the same thing to create a list of those hashes. Alright, so you can see, not hashes, but the ciphertext and the plain text, you can create a list of those, a JSON list of those. You can get the hints for a particular ciphertext. You can also get the hints for pieces of it. I'll show you how to do that here in just a minute. You can run a statistics gathering method against the database itself, and then of course you have the ability to update hashes once you actually crack the plain text. So let's go back now. Let's pick a target, and I need to find out. I actually picked somebody already, and I need to know who this is. Give me just a second, because I went through and found one that works out well. Okay, his name is Hans. Or that's at least what his email address starts with. Show credentials. Let's go in here and let's scroll up to Mr. Hans. H-A-N-S. Where are we at? Okay, there we go, right here. This is the guy. Alright, here's his base64 encoded password. So what we want to do is we want to reverse this thing here. Okay, this is what we're interested in. Let's go back over here and we'll do our c.get hints. And we'll type in the entire ciphertext and hit enter. And it's going to go into the database. It's going to pull out all the hints that are related to that particular ciphertext. And there's 3,277 hits there. Okay, so we start looking down the hints. What do we notice immediately? Right? And I know that I went through and I kind of cherry picked one, but it only took me 4 tries to find this one. Literally about 50% of them are this easy to crack, right? 1, 2, 3, 4, 5, 6, twice. 1 through 6, 2. 1 through 6, twice. That's the top of the list. Let's scroll down to the bottom and see if the hints get any better. Right? 1, 2, 3, 4, 5, 6 times 2. If you speak Spanish, these probably says the same thing. Memo, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Do you know how often the actual password is the hint? Like pretty often. I actually want to go through and do some statistics on that because I have found in most cases there are multiple hints within the hint list that actually are the password themselves. So it's pretty interesting. Okay. So we're guessing that's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, right? Once we know that, we can do C, what was it? I can't remember what the name of my own method was. C.update hash. Okay. C.update hash. Put that in there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That looks right, doesn't it? Okay. Update hash. Now, once I've updated the hash, the database is now, that ciphertext is cracked. What I do now is I run the get blocks database, and what that will do is that will go in, it will take every single ciphertext that's been broken down into plain text, it'll separate it out into hexadecimal characters, it will take that block, assign it to plain text, and write it to a JSON file. And so I now have a JSON file. Once I do that, it'll take about 15 minutes to run it here, so I'm not going to do it. But once I did that, you would have a blocks.json file, right, that's got all those blocks in it. So what do we do with that? Well, we wrote a module for recon-ng that takes that blocks database, right, it goes through your credentials table, tells out all of the Adobe ciphertext, right, and then it takes the blocks database, it applies it to it, and it cracks passwords. Okay, so let's go ahead and look at that now. Jump back over here to recon-ng. I'm going to load Adobe. Show info. Block database is already there. I distributed this with recon-ng. I've been kind of quiet about it, but I added this about a month and a half ago. And I've been updating the block database as I crack more passwords. Alright? And so let's go ahead and run this and see what it does. Alright, so we see right off the bat, most of these, you see a lot of asterisks here. I'll talk about that in just a second. Some of these were not cracked. Those that were partially cracked, you'll see blue with some information. Like here, you see an unknown block, a padded block plus a 9. And then down here, you see we actually have some of the clear text ones that are cracked. Really, really, really basic ones. So what does this mean here? The 8 asterisks means that I can confirm that the length of the password is 8 characters, even though I don't know any of the plain text within that block, because it ended with that null byte and then padded it out to that second block. And that's common throughout the entire database. So it's really easy to determine when I have an 8-length password, a 16-length password, a 24-character length password, and so on and so forth. All right? So I'm starting to track passwords now, because they use the wrong mode. Okay? That's all it takes. One little slip up, and now you got somebody busting up the passwords. So let's go back over here to the presentation now and continue on with this. So what are some solutions to this? One, use a strong key. Right? Adobe did that. It didn't work out so well for them. Number 2, store the key in a secure and accessible location. This is really, really hard to do. Has anybody tried to do this before? I mean, were you successful? No. And I'll tell you what, I only say it's not impossible because I don't believe in absolutes and security. I just simply don't. Every time you say it's impossible, somebody does it, right? And then they rub your face in it. So I'm not going to do that. I'm not going to say it's impossible, but I will tell you that every single mobile assessment I do, they try to hide something on the phone. They try to hide a key somewhere. You can put it in the key chain, you can put it anywhere you want, but if I jailbreak that device, I own it, and I can get any piece of data I want off of it. And I've never seen a key stored in a way where I couldn't break it if I was able to escalate privilege. Okay? This is hard to do. It's not as easy as it sounds. It's tough. Okay? Next thing is use cryptographically strong algorithms and cipher modes together. Okay? If you can do all 4 of those things, you might be in decent shape, but it's difficult. Why not just hash your passwords? Hashing is so much simpler. Okay? Still right off the bat, it's simple. Here, my pseudocode, I pass the password, here's the hashing algorithm, I got a protected form, bam, I slammed it into my database. It's that simple. Okay? But is it really that simple? Let's talk a little bit more about the characteristics of this storage system. Okay? There is no password recovery system. Remember, hashing is irreversible. Cryptographically irreversible, I should say. Cryptographically irreversible, because we can guess things, right? We can guess plain text, hash it, compare it, and try to crack it that way. But cryptographically, they're supposed to be irreversible, which means you cannot use the algorithm to unhash it, okay? So, therefore we can't recover the password, but we can design a reset system. And this is a little bit more complex than a recovery system because it involves someone authenticating themselves in some way in order to reset their password. Okay? But there is a way to do that. It's just a little bit safer because now we're not recovering the original plain text. Predictable resource requirements. Finally, we have some predictable resource requirements. And the reason being is because hashes have what? Fixed length output, right? No matter what you cram in, it's always going to be the same length on the output. So now you can have a 10 gigabyte password. Guess what? User child 1 is going to be 40 characters long. So you know you've got predictable length output here, so you know what your resource requirements need to be based on how big your user table is going to be, and therefore you can allow unlimited length passwords, any character you want, as long as you're not vulnerable to SQL injection, right? Just be smart about how you develop the system. But basically, unlimited length passwords here. This is a much better solution in terms of password strength, security. Right? And once again, the results should be cryptographically irreversible. So what are some of the problems we have? Well, all I got to do is create one lookup table for the hashing algorithm you're using, and then I can crack passwords with it. I can try to reverse those, not cryptographically, but I can just create this huge table that takes every possible value between 0 alone and whatever the word is at the end of a 15-character rainbow table, right? Create this huge lookup table, and then apply it to your hashes and reverse them that way. Okay? The other thing is that these types of hashes are likely indexed by search engines or collected by hash collectors. And we'll talk more about that here in just a moment. What's a good example of this right here? Stratfor, December 2012. They hashed their passwords. 860,000 of them were disclosed to the internet. Do you think there was any risk in those being reversed? Absolutely, there was. I'm going to show you right now. All right? So let's do it. What does this look like? Going back into Recon NG, I want to show. Actually, I should just do this. Okay, so I got 4 modules, actually 3 additional modules other than the Adobe module that works on cracking credits. All right, BozoCrack, Patches.org, and LeakDB. All right, BozoCrack. Anybody heard of BozoCrack? It's a neat Python script that came out earlier this year that says, hey, you know what's really funny? You can search Google for a hash and then take every word in the HTML response, hash it, compare it to what you searched for, and Google will tell you if it knows about the solution of that hash. That's a great idea, but you're only implementing ND5. I took that and I implemented every single hashing algorithm that Python supports It goes through, it searches Google for that hash, it takes the HTML, it parses out every single word in the response, hashes them all, and compares it, and tries to find out if Google knows about that particular hash and what the plain text is. Right? So we've got that one that does it that way, it uses search engines. And then hashes.org and LeakDB are hash collectors. So when people crack hashes, they can submit them to these resources here. I'm pretty sure these guys are also doing some hash cracking in the background on their own, right? And since there's no salt involved, it's going to, if we hash it locally or they hash it there, the output is the same, right? So we can go and we can look at we can use their APIs to actually look up the ciphertext or the hash. I'm sorry, look up the hash to see if they know what the plain text is. So let's run a couple of these modules. The first one I want to run is the bozo crack module. Run it. This one takes a little bit longer because it's having to do all that hashing and comparing for every single word that's in the result. So we'll let it find one of the results just to kind of show you that it does work. And then we'll move on to some of the other modules. There we go. All right, found one there. Pretty cool, right? We got one way we can reverse these hashes. And by the way, these hashes are all coming from the creds database. All right, it's pulling all of those, everything it recognizes as a hash from that creds database, and it's now using those as input for this particular module. So let's load, let's do LeakDB next. On this one, these are much quicker. The APIs are a little better. Guy's an Indiana fan. Football season sucks for that guy. Alright, so LeakDB, we've got one additional one. Let's load hashes.org. Run this one. This API is really good. Let's just submit 20 at a time. So, bam, he's busting these things open. What does this tell you right here? When you start seeing results like this? Does it tell you anything? Randomly generated passwords probably on behalf of the user, but this guy's probably cracking hashes in the background. These are all short enough that he's probably got a lookup table, and he's looking up your hashes. I would almost guarantee it. Yeah, either that or there's by some off chance these are all collisions, which I highly doubt, right? But it's a possibility that there are collisions and they're using some sort of salt, right? There's some sort of salted hash and there's a collision there, but I doubt it. It's probably brute forcing them and the user using random passwords. So this is the risk. You might have hashed your passwords, but I can still find the plain text of some of those. Okay, so we still have a risk here. We're still not immune from attack. So let's continue moving on here. We're running out of time. So what's our solution here? Well, let's try salted hashes. Salted hashes is a little bit different. We're introducing some randomness into the hashing process to solve a couple of problems. And this is what the pseudocode looks like for that. So what are some characteristics of this? Well, it shares all the same characteristics as your previous hashing does, except it adds some new things to it. One, theoretically safe from recon NG. Because if I'm hashing, right, if I'm salting my hashes, there's probably a decent chance that no one else out there that's creating hash tables and making them available is using the same exact salt that I am. I've not encountered any API that says, hey, submit your salt and the hash. We're doing all this in the background. I've never seen any of that. So theoretically, it's safe from the recon NG style attacks that I've been conducting. Okay. The number two, it conceals identical passwords, and we call this parallelism. So what does that mean? Remember, hashes, same input equals the same output. So if I break into a database and I dump the contents of it, and I see this person uses this hash and his password is this, I can look for all the instances of that same hash and know that person's password. Well, this prevents that now as long as we're using unique salts. Because you can have the same password, but as long as your salt is different, when it gets folded into that hash, the result is different, and therefore we have no parallelism in terms of what the clear text of the password is. Okay. So those are really important distinctions. Okay. What's the problem here? Well, you have one lookup table per salt used. So if you're not using unique salts, this is a problem. How many people here have seen this implemented where the developer used the same salt for every password? Is that more or less the same as regular hash? Same, right? All you do is the same thing. If I got the hash, that's super easy, right? Also, algorithms such as SHA-1 and ME5, the ones we see typically used here, those are designed for speed, right? As hashes are designed for speed, which makes the offline attacks much more effective against those particular algorithms. Okay, so an example we have here, I have no idea how to pronounce this. I need to look it up. I can't figure it out. right? But they're the developers of the Cydia project. For those of you that deal with iPhone jailbreaking, you're probably familiar with Cydia. In 2014, this year, a couple months ago, they got breached, 100,000 accounts were dumped, and I've not found an instance where any of those passwords were cracked, right? Any of those salted hashes were cracked. However, it's still possible. It's still possible because we can still conduct offline attacks against them. So what are some solutions to this problem? Well, make sure each salt is unique, right? And make sure the salt is cryptographically random. Right? That's one solution to this particular problem. And if we're doing that, we're in pretty good shape. But we still have that speed problem. So the solution to the speed problem is using adaptive hashing functions. So what does adaptive hashing functions look like? Okay, well, once again we got an algorithm, we got a salt, so we're preventing that parallelism by using a salt, right? And then we introduced this new factor called rounds. Okay, and this is where work factor comes in. I'll talk about work factor here in just a minute. But as you can see, our hashing function, it takes the password, it takes the salt, takes the rounds, and it gives us this nice clear text value we can store in our database, and it does it slowly, right? Which is really, really nice. That's what we're after. Now, how do we break this down? You can see the difference in information in here we can pull out of this. The first bit, the dollar sign is the delimiter here. The 2A, that's the version of Decrypt that was used. So version 2 alpha of Decrypt. The number of rounds here, 12. And then the first 22 characters of the hash itself is the salt, and then the remainder of it is the actual result of the hashing function. Okay. All of this information, it's okay that they know that. It's okay that they know this, right? Because of that salt, they're still going to have a more difficult, they're still going to have a separate lookup table for every single one of these hashes. But because we're using a slow hashing function, an adaptive hashing function at 12 rounds, it's slow enough where it makes offline attacks unreasonable. Okay. So what are some characteristics of this? Well, it dynamically increases the work factor. So the rounds thing is extremely important. Okay, all of our web servers or wherever you're storing this information, wherever these hashes are being, wherever this hashing function is actually running, right? It's going to have different resources than say another server. So what you have to do is you have to tune these things so that they take just as much time to make it a problem for people that are trying to hack these things offline, right? So you make it slow enough that it affects those people, but fast enough that it doesn't mess with the user experience. So if you go to log in, you click submit, it takes a second for it to go back, do the hashing function, and respond. Does that bother you as a user? No, that's not. It's fairly unnoticeable to a user. But to somebody that's trying to crack hashes, that is all day, right? That destroys their ability to conduct an offline attack against this. So you have to tune the number of rounds based on the function that you're using, because there's 3 different adaptive hash functions. And I encourage you to go out and research those. You have to tune it so that it works optimally on your configuration. Okay, but that's the main difference between the hashes, salt hashes, and now the adaptive hashing functions. So what are some problems here? Well, support. Not all of our programming languages support these readily. So that may be an issue for you depending on what language you're working in, or perhaps you could write one. All right. If you're not a crypto guy, don't do that, please. Dictionary attacks against weak passwords. So the thing about this is every single method we've looked at thus far is still susceptible to offline attacks. So we've gotten slower and we've made it harder, but offline attacks are still possible. Because even though it's slow, I can take a reasonably decent dictionary, I can use your Decrypt with your 12 rounds or whatever it is, and I can still try to crack passwords. And I may or may not be successful, but it's still a valid attack. Right? Well, there's only one solution to this, and that's ball and chain. And I'm not going to tell you what ball and chain is today, because two weeks from now at DerbyCon, a guy named Benjamin Donnelly and myself are going to release a technique that's going to change all of this. It's going to make offline attacks against passwords completely impossible, and we're hoping that it revolutionizes information security from an AppTech standpoint. So if you can be there, awesome. If not, it's okay. But check out the video if you don't go, because this is some serious stuff. It's all Benjamin Donnelly came up with the technique. I'm just helping them market it. But this is going to be the solution moving forward. If you're not, until 2 weeks from now, do this. Okay? Until 2 weeks from now, use adaptive hashing functions, and then 2 weeks from now, use ball and chain. Okay? But the point here is, there's still not a perfect solution, but we're working on it, and we're trying to get there. Okay? So here's some statistics about what I did. I went and published. I said, show me all the information about all the dumps you've got. I want to see stats on it. So as of September 4th, this is what it showed me in terms of the types of storage that's being done against the password databases. And so far, we can see that these obsolete fast hashing algorithms are used a lot, right? I mean, look at all these MD5s and these SHAs. Right? Those are fast hashing algorithms, and they're being used quite frequently, which tells us what? that people don't understand the purpose of those hashing functions. Those hashing functions are designed to be quick. We want to slow the process down so we can prevent offline attacks, right? And so then we go look and say, well, who's doing it right then? Well, there's two people. In thousands of them, there's two people using bcrypt. No one's using scrypt, and no one's using the other one, which is a couple different letters that start with PD, I think. But anyway, I can't remember the name of the function itself. I never can. But there's three popular ones. There's only two people that are actually applying that. And if you look at the thousands of blanks, like you see the one dash up there, you see the blanks, you see this NA right here. Of those thousands, those fall either under the salted category, the plaintext category, or unknown. And I don't know what unknown means, but I'm thinking unknown means probably plaintext. Okay? And so I did a search of all those thousands to find out how many times salt showed up in the description, and it was 30 times, which means most of those thousands of dumps are clear text. All right? This is still a problem. It's not getting any better. This is just a week ago or so. All right? So this is a huge problem, and we've got to fix this moving forward. All right, to summarize, all right, encoding is not encryption, is not hashing. You've got to teach your developers this stuff. And if you're a developer, you got to go out and learn this stuff. All right, this is critical because it's going to factor in how you implement these systems. Okay, use the different random salts and slow hashing functions when you're storing credentials. Okay, until next week, this is the way you need to do it. All right, and then if you don't feel like implementing ball and chain, continue to do it this way because it's the safest of our other available options. All right, help me reverse Adobe cipher blocks. I'm going to put the database on a USB stick. All right, if you want it, it's about 9 gigs. If you want it, I'll provide that database to you so you can help me start cracking these things. All I ask is that you run that create blocks DB method and shoot me the blocks that you crack. All right. So we can talk more about that, addressing individually if you're interested in doing that. At 10:35 if you can for the release of ball and chain, that'll be really, really cool. And always design your password storing systems, assuming that it's eventually going to get compromised. All right. Always do that. If you're doing that, then at least you're approaching it with the right mindset. Okay. So that wraps it up for today. Thank you guys for coming, and go Fox.